Hey everyone. In this video I'm going to talk about how we can use regression and linear modeling for causal inference to analyze randomized experiments. Okay, so as I mentioned in the previous video, in the usual regression context, the way we kind of talked about predictive inference, we focused on comparisons between units. Okay, and in causal inference, what we're focused on is basically comparisons of different treatments if applied to the same units, right? That's ultimately what we're trying to estimate as a difference between the factual and the counterfactual outcome for each individual unit, and then averaging over all of the units. Okay, so in that case, in that sense, since we're basically since we only observe one of the potential outcomes and we don't observe the counterfactual outcome, in that sense, causal inference can be viewed as a special case of prediction in which the goal is to predict what would have happened under different treatment options. Okay, and in that sense, we can use kind of our techniques from regression and linear modeling ultimately as a prediction task in order to provide causal inferences, to provide estimates of our treatment effects, okay, in comparing treatment and control groups, okay. The key, of course, is that in order to make these causal inferences, we need stronger assumptions than for pure, predictive inference and purely predictive tasks, okay. The example that we're going to work with is based on an intervention that consisted of an educational television show that was given to students from grade 1 through 4. Okay, and what we're going to do here is I'm just going to briefly give an overview of that data, and in our Q&A session we will then actually go into analyzing these data and looking into a lot of these considerations regarding estimation, including pre-treatment covariates and so on, in the Q&A session in our live coding session. Okay, but here a quick overview of the data that we're going to use. As I mentioned, this is an experiment where different classes were assigned to watch an educational television show, and the outcome of interest is basically reading comprehension or reading scores. Okay, so we have different classes. Each of those classes basically completed a reading test before the intervention and after the intervention. And some of those classes were assigned to the treatment group where they actually viewed this educational television show, and some of those classes were assigned to a control, so they didn't view this educational television show. So our substantive question is, of course, whether this educational television show was effective in increasing reading comprehension, okay, or reading scores. Okay, so what we have here is we basically just look at histograms of this outcome of the post test reading scores in grades 1 through 4, comparing the control group on the top and the treatment classes or treated groups in the bottom. Okay, and just by visual inspection, we see here that especially for lower grades, there seems to be an improvement in reading scores for classes that were assigned to the treatment, to the intervention, so to the educational television show. Okay, so of course, rather than just analyzing this visually, we want to ultimately provide an estimate of how much of an effect this intervention ultimately has, whether it can be assigned, whether it can be attributed to just pure chance, or whether there's actually something more systematic going on. Okay, and so based on our discussion of average treatment effects and causal inference in the previous video, of course, the assuming that the treatment assignment was purely random, we can of course estimate the treatment effects by comparing the mean differences between the treatment group and the control group, right? So we can look at a basic difference in means estimator to estimate the average treatment effect. Okay, so one way here would be to just run a t-test for our post test reading scores, comparing the treatment and control group, and we will see, okay, we have a difference in treatment in reading scores of around 8.3. Okay. So this is a basic, comparing treatment and control averages, a basic difference in means estimator. The key here is that we can recover the same treatment effect essentially using linear regression, and obviously we recover the same kind of patterns using linear regression, because if you remember, linear regression ultimately helps us estimating conditional averages for our respective predictors. Okay, so here we have a basic linear regression. Our outcome is the post intervention reading score. Our independent variable is just our treatment assignment, which is 0 or 1. Okay, so in this context, using this experiment, using this experimental data, our intercept is then our basically expected outcome, our expected reading score for observations or for classes that were assigned to the control group. So that's 68.9, which is of course the expectation in our control group. And then the coefficient for our treatment indicator is then the difference in the expected outcome for observations where this treatment indicator is equal to 1 versus 0. So that's the difference between treatment and control, or in other words, directly the treatment effect itself. Okay, so this is 8.2. There's just a slight rounding deviation, which is equivalent to the mean difference that we recovered here based on the difference based on the t-test. Okay, so 8.3 increase in reading scores. Here we have an 8.2 increase in reading scores based on our linear model. Okay, so in that sense, we can recover exactly the same results using linear regression that we had using a basic difference in means estimator. Okay, but of course, basically using linear regression or using linear modeling provides us with additional opportunities to basically improve our estimates. Okay, because we don't only have to include our treatment indicator to recover basically exactly the same as the difference in means estimator. The key here is that in our linear modeling framework, we can include additional control variables, additional pre-treatment predictors that will help us provide a more precise estimate of our treatment effect, and will also allow us to, for example, characterize conditional treatment effects in more easily, essentially. Okay, so ultimately, what we're going to do in our Q&A session on Monday is basically analyze these experimental data using different regression models to not only recover this difference in means or this basic average treatment effect or the sample average treatment effect, but ultimately use additional covariates, expand our model to increase precision, and also make sure that we truly have balance between our treatment group and our control group. Okay, so just to conclude, a couple of just general pieces of advice for causal inference using regression or when analyzing experimental data with linear modeling. The first big advantage over the simple difference in means estimator is that if you're using regression to analyze, or linear modeling to analyze your experimental data, you can use pre-treatment covariates, or you can control for pre-treatment covariates, which will achieve two crucial things. One, it will basically make sure that there's balance in those pre-treatment covariates between the treatment and control groups, and it will increase the precision of your estimates. Okay, You can also directly estimate varying treatment effects conditional on these pre-treatment covariates. So basically, you can include interactions between your treatment effect, your treatment assignment, and these pre-treatment covariates to directly model varying treatment effects. Okay. And then the next step, and we already talked about post-stratification. If we're interested in not only our sample average treatment effect, but interested in extrapolating that to a known population, okay, we can use the same techniques of post-stratification to ultimately provide estimates for our population average treatment effects, right? So in particular, if we include interactions for each of those, for important social demographics, age, gender, education, and so on, we can use those interactions and those conditional treatment effects to then make or provide estimates for treatment effects in the population based on our linear model estimates. Okay. Another important thing to keep in mind, while it is always advisable to control for pre-treatment covariates to increase the precision in your estimates when analyzing experiments, you should never adjust for post-treatment covariance. So you should never adjust for outcomes that basically are potentially affected, that are measured after the treatment assignments and are potentially affected by treatment assignment. Because ultimately that will basically lead to imbalance between your comparison between treatment and control group, and therefore bias your estimates, and you will not be able to recover any meaningful causal treatment effects anymore. Okay, so never adjust for post-treatment covariates when analyzing experiments using regression. Okay. And the last point is just to be careful with classic mediation analysis. So in a lot of kind of experimental work, what we're ultimately interested in is not only the treatment effect itself, but we're also interested in why this treatment, or through what mechanism a certain treatment impacts an outcome. Okay, and so one kind of classic approach in mediation analysis is then to include this mediator in a linear model and then examine whether the treatment assignment itself still has a significant effect after controlling for the hypothesized median mediator. Okay. The problem is here, again, this is a problematic strategy where you ultimately induce imbalance between treatment and control, and you will not really be able to recover any meaningful causal effects, or really quantify how much of this effect was mediated through your mechanism that you hypothesize. All right, because that would require a lot of additional or strong additional assumptions about sequential ignorability and so on. Okay, this is only briefly mentioned in our required readings, but if you're more interested in mediation analysis, I really recommend you to take a look at the EMI paper that I included on Canvas as well, which talks a lot more about kind of this critique of classic mediation analysis, why it's potentially problematic, or why it needs a lot stronger assumptions than is often kind of appreciated in the literature. And it also provides kind of alternative estimation strategies instead of using this kind of classic mediation approach where you just include the mediating variable in your model itself. Okay, so for us here, just in general, be careful with mediation analysis. Identifying mechanisms, even in a randomized experiment, is incredibly difficult, requires much stronger assumptions, and it's not achieved. These assumptions are not met by simply randomly assigning a treatment and a control, right? We need a lot more to identify the underlying mechanism, okay? So just something to keep in mind if you're running experiments, if you're designing experiments, and you're interested in identifying mechanisms. There's a lot more that kind of goes into the design and the underlying assumptions and in the estimation to ultimately conduct these mediation analysis. Okay. But for now, this should be enough for us for this week. As I mentioned in our Q&A session, we're going to dig into the data and actually run some models to estimate different types of treatment effects, as we discussed now here in this video and in the previous video. And so I'm looking forward to our next Q&A session.